Okay, it's ready to go. Okay, so we're going to talk a little bit about electric fields, okay? Now, you probably have very little familiarity with fields right now. The way this course is laid out, we haven't really covered fields in general, so we'll just talk a little bit about what a field is uh, first off, and then we'll specifically talk about electric fields, okay? So, fields is actually short for force fields. And so this sounds pretty, science fiction-y, but in reality, what it just means is an area, in this case around a charge, where other charged objects experience a force. Okay? You have probably experienced force fields if you've ever played with magnets, or you've ever, charged up two objects with the same charge and put them together, or felt the attraction between two oppositely charged objects. You probably did that a lot with your experiments and stuff that you did back in grade 9, right? Also, interestingly, we live in a force field, and that force field is the gravitational field around the Earth, and it acts on mass. So what you're probably getting from this is that different types of force field act on different types of charge. So force fields are, it's a little hard to explain in one good sentence, but areas where a force is experienced by X. X just being whatever it is that we're talking about, okay? So before we move on, let's talk about the 4 fundamental forces that are found in nature. Do you know what they are? What are they? Did we talk about them before in this class? Good. So gravity is one. There is electromagnetic. And there is the weak nuclear and the strong nuclear. For you and I, we mostly deal with this on a day-to-day basis, okay? So these affect the large-scale world. And we can, interact directly with them. Okay, these are a little less obvious. The strong nuclear essentially exists within atomic nuclei and is responsible for making atoms stable. So if you look at the periodic table and you see the fact that hydrogen only has a proton, okay, fair enough. But then when you move up to helium, there's 2 protons, and we kind of understand that electrostatically those positively charged protons will, be pushed apart due to the electrostatic force field around them. However, there are 2 neutrons in there, and actually the protons themselves exert strong nuclear, and that essentially, I guess, acts as a glue to hold an atomic nucleus together. The weak nuclear force, as I understand it, and I don't really understand it that well, but as I understand it, acts counter to the strong nuclear force and serves to push apart unbalanced nuclei. So if you have too many neutrons or too many protons, such as you might find in some heavier elements and isotopes of stable elements, they will become unstable due to imbalances between protons and neutrons due to the weak nuclear force. Oh, I don't think the door's closed. You got to give it a good yank. Okay? So that's what that is all about. Okay, so we'll quickly talk about gravity just in the sake, since just because we're talking about force fields, and it's a pretty obvious one to talk about. So go to gravity field really quickly. There is a unit on fields that we'll be doing after this, where we'll talk about it in much more detail. But the general concept is this, okay? Say we have a mass, and it could be a planet, or it could just be really anything. What ends up happening is between these two, there exists an attractive force, which we call the force of gravity. And it turns out that Newton was able to figure out that that obeys an inverse square relationship. Okay? And we've talked about inverse square relationships before. We talked about what happens to the light of stars as they, emanate out into space. And geometrically, basically what goes on is as the area that the emitted light, covers gets larger and larger and larger, right? As you go, outward, if you were to imagine there's like a shell here, traveling out into space, as it expands outward, right? The area through which the light passes, I didn't really draw that very well, but you see it expands over a larger and larger area, and so this area gets bigger, and the amount of, we'll talk about force lines in a second, passing through it gets lower and lower. The density of force gets lower. Or, if you want to talk about light, the intensity of the light gets dimmer, and it gets dimmer at a square to distance, and it's just a geometrical relationship. It's nothing particularly outrageous or difficult to understand. It's just what happens to the surface of a sphere as this surface gets larger and larger and larger. Okay? So let's talk about lines of force, because they're going to be important. So we're going to represent something that's actually three-dimensional on a two-dimensional page here. I wonder if I can. Uh-oh. Oh, I don't like that. So what are these? Well, these represent force field. Existing around an object. So if we think about it, if this is some mass, we know gravity is always an attractive force. We know that in any direction that we travel around this object, and you have to imagine that it's in 3D, so into and behind the page in all dimensions, what you're going to find is you're going to find that the force will always be directed towards the center of the object. I think we've probably basically covered this before. All of these converge, right? If you were to extend these lines into the interior of the object from all different directions, they will come to basically a focus at the center, and that's what we call the center of mass or center of gravity of an object. Okay? So now wherever we place another mass, if you want to call it a test mass or a small mass, all right, the force experienced is shown by this vector arrow. Okay, these are called lines of force, and it's how we represent force fields. It's easy for gravity. Gravity is always attractive. It will always be a force towards the center of the object. So, does a gravity field? What does a gravity field work on? It acts on what? Yeah, it acts on mass, right? So if an object doesn't have mass, then the gravity field really doesn't apply. It's kind of one of those, like, if a tree falls in a forest, does it make a sound type thing? If there's only one object in the whole universe, right, it has a mass, is there actually a gravity field there? Because there's no other mass available to detect it, so you wouldn't really know, right? What objects don't have mass? Depends on your definition of object, I guess. I'm thinking a photon doesn't have mass. However, photons can be deviated on their paths because of gravity fields. So you're getting into something that's a little more advanced than the way we want to talk about it. And that's like the warping of space-time and so on. I know you want to get into that, but it will derail us, and I don't know enough to properly explain that to you. But for all intents and purposes on Earth, you know, paths of light or paths of photons travel in straight lines. Laser beams do not bend, you know, due to Earth's gravity. They may bend a little bit due to density, you know, something along the density size of a big star or a black hole or something like that. And that's where you get this concept of gravitational lensing, right? Light is refracting literally around the gravity fields. But hey, let's not go there right now. So this is the concept of a field. We're in a field. We can detect the field that we're in, and we essentially feel that as weight, right? Really what we feel as weight is the normal force of the ground pushing back up on us as the Earth pulls us towards it. Okay, that's what we feel as weight. We call it apparent weight because it goes away, right, when you're falling, doesn't it? You can't feel your own weight when you're falling. So the weight that you actually feel, what we call weight, is really a reactive force. Is the normal force pushing up on you. And you can feel changes in this when you, say, go in an elevator and it starts accelerating. You get that loop in your stomach as, you know, the normal force changes and your weight literally changes. Does that make sense? Your apparent weight literally changes. Your actual weight doesn't really change much, okay? It only changes when the gravity field changes. So if you move outward, right, from the Earth, the pull of the Earth's gravity on you decreases and decreases and decreases. So let's look at electric fields now because they share some similar properties. There's not a lot of relationship, at least figured out so far, about how electricity and gravitational fields are connected, how you can have the same physics that describes both. But the fields themselves and how they work is somewhat similar. So let's talk about electric fields. You guys like this color? It's quite invisible, hey? Okay, so electric fields are oh, yeah, and one more thing. Units of measure are kind of important. So let's talk about this quickly. Units of measure. How do we measure the strength of a gravitational field? And there's actually two sort of ways. There's one way that we're used to, and one way that's going to be kind of new. So the way that's kind of new is going to be newtons per kilogram. How many newtons does each kilogram experience on Earth? And can you tell me an answer to that? How many newtons does each kilogram experience on Earth? About 10, yeah. So essentially 9.8 roughly. 9.8 newtons per kilogram. Now what does that look like to you? What is that magic number? Yeah, it's also the acceleration due to gravity, and I can just show you here quickly that it is in fact the same units. So how do we pull apart a newton into its basic units? What's inside a newton? Right? Per kilogram. So these are essentially equivalent units. All right, so the field strength of any, you know, massive object, or any object really, is measured in newtons per kilogram. Okay, so how many newtons do you get for a kilogram? And remember, we're talking right near the surface of Earth, because that number will actually start to drop the higher up that you get. It's not appreciable, say, from the bottom to the top of a mountain, but by the time you start getting out to where satellites and such and so forth are, you know, gravity might drop to, say, 8 or less, right? And as you go farther and farther away, it decreases and decreases. Is there a place where it would go to 0, do you think? No, that's correct. It's sort of an asymptotal relationship, and if you look at the equation, back up here, right, as this number grows, this number gets progressively smaller. So what does the relationship between gravity and distance look like, assuming these things all stay the same? What would that be shaped like, do you think? As you oops, holy, it's hard to draw a straight line. As you fly away from the Earth in your spaceship, what happens to the force of gravity? Right. get that. Okay. Force of gravity, distance. As distance grows, force of gravity decreases, but it will never reach zero. Okay? So that's interesting, right? What that means is, you know, if say there's only 2 objects in the whole universe, like, you know, you and your best friend, no matter how far away in the universe they are, their gravity will still affect you. Isn't that a comforting thought? No matter how far away they are, their gravity is still affecting you. Oh, is it? I haven't seen it. Yeah, don't ruin it for me. I haven't seen it yet. I have no time to watch movies these days. It's very sad. Very, very sad. Okay, so... yeah, I can tinker on my fan thing and still watch my kids at the same time. Whereas I can't go to the movie theater and watch them at the same time. Okay, so newtons per kilogram, right? Newtons per kilogram is how we measured gravitational field strength. So what we want to know is, how might we, or how do you expect, do you think, that we might end up measuring electric field strength? Don't answer that yet, but just keep it in mind. Okay, just keep it in mind. So something that you probably are aware of is that there are 2 types of charge. There's the positive type, and there is the negative type. Okay? Positive is carried by protons, the negative by electrons. I've drawn them the same size, but in reality, they are physically not the same size. What's the size relationship difference between these 2 things? If we say, just talk about masses. Yeah, if you make this 1, this has to be 2,000 in terms of mass. It's like 1899 or something, but roughly 2,000. So it's much bigger. Okay, we know that if we were to look at an atom of some kind, not an atom, no, an atom. So this should be review in an atom, right? We have a whole bunch of protons hanging out inside here, along with some number of neutrons that happen to be more or less correct to give this stability. What do we call atoms or atomic nuclei that have the same number of protons but varying number of neutrons? Isotopes. Good, good. So in nature, right, we remember that there's a blend of different isotopes in a pure sample of something. So we're just going to try to simplify and say, okay, well, if I have plastic, like for instance, because plastic makes a nice insulator, so you can actually store charge on things that are plastic. But in this plastic, we have atoms that then make up molecules that in their very core have positive nuclei. Even though there might be differing numbers of neutrons, that doesn't really change too much what happens with the electricity involved here, right? And then outside, we have a balancing number of electrons. So in this case, 1, 2, 3, 4, 5. Ooh, how many did I put? 8. So then we're going to have shells, right, with our electrons out here. So what did I make here? What is this? Is it? Yeah, okay, oxygen. Well, maybe not the best example, but yeah, this happens to be oxygen. What do we call these outer shell electrons? Now, I hope like a real solid-state physicist never looks at this, because it's probably not. I'm probably not telling you things exactly how they're supposed to be, but for our understanding, this will be good enough. Okay, these guys are the interactive part of atoms. Okay, unless you're a nuclear chemist or a nuclear physicist, you don't really need to worry about this. Besides understanding that it contributes, plus 8 total charges. Okay, and what we can do is we can actually ionize this in a few different ways. Now this might not be the way that it works chemically, because this is sort of an accident that it happens to be oxygen. But what we'll notice is we can add extra electrons to the outside. So we might have this, or Alternately, we could potentially take electrons away, and then we have an imbalance in the other way, where we get this, okay? So you can ionize these things. Now there's one way that tends to happen in nature, and that is oxygen actually gaining 2 electrons to fill its outer shell and getting a -2. But we're not really talking about it in terms of the point of chemistry. We're going to be just way more general in how we talk about it in terms of overall objects. So let's say I have an insulating rod, and then I realize this is just review, and that's good. It's good to have review a little bit. Let's say we have a cloth. It's also insulating. So this will work with a plastic ruler, and this could be your t-shirt or rabbit fur or something. You'll find that if you rub the insulators together, there's going to be a charge transfer. I should probably, maybe you want to write this down, I'm thinking. Depending on what the objects are, you will get a transfer of electrons from one to the other. In fact, at the very dawn of the understanding of electricity, Ben Franklin was rubbing one object on another, and I believe it was glass and amber, and something odd happened in that he called one positive and one negative arbitrarily, and it turns out the one he called negative actually had the literal positive charge on it. So what you have is you have an inversion of what's actually positive and negative. And I'm just going to see if I can quickly find what I'm looking for, because there's a funny comment. So here it is. It says, Ben Franklin. Yes, I bring a message from the future. I don't have much time. What is it? The convention you're setting for electric charge is backward. The one left on glass by silk should be the negative charge. So is glass and silk. And it says, we were going to use the time machine to prevent the robot apocalypse, but the guy who built it was an electrical engineer. So in other words, when you wire your house, right, what you're calling positive, right, basically we say, right, when we look at a battery, that charge flows from the positive terminal to the negative terminal. So the way we're looking at it then is must be that positive charge is flowing. However, if you look at, the atoms that we just drew, we see that positive charge can't really flow. It's locked away inside the nucleus. So it must be electrons that are actually flowing. And I think that that's well understood, that it's electrons that are flowing, but you might ask yourself, well, why do we show it positively and why do we show it negatively? The reason why goes back to the days of Ben Franklin experimenting with electricity, rubbing glass on silk, noticing that they attract, calling the wrong one positive and the wrong one negative. All right, and we've held on to that till now. So it's a historical anomaly. I'm wondering why positive and negative. Why not, like, it could have been anything, right? Why not red and white or black and blue charge? It could have been anything, right? And then it wouldn't have mattered quite as much. Assuming, I guess, that, yeah, I don't know exactly what the deal is, but anyway, that's kind of the history of conventional current versus electron flow. Okay, so as we rub, right, one of these has, I guess, a larger affinity for electrons, so let's just say that what ends up happening is a few electrons get pulled off of the insulator and onto the rod. What you will get is you will get an area on this rod that has negative charge, and you'll get an area on this that has positive charge. Electrons are the only thing that can move, so this is a loss of electrons that makes this thing positive. This is a gain of electrons that makes this thing positive. Okay? These have to be insulators. If they're not insulators, all right, if it's metal and you're holding it, okay, what you're going to do, there's your hand, it looks like a crab claw. What you're going to do is you're going to ground out the charge, okay? And we know from past experience, right, that like repels like. Okay, so in this case, these negative charges that you've kind of put together in one spot repel each other, and you'll get charge pushing down into your body and off of here, and it will not stay charged. Conversely, if this is also a conductor, okay, and we have a ground here, charge will flow up in order to neutralize because it will be attracted. Opposite charge will be attracted. Like repels like, and opposites attract. So this is all grade 9 physics in a nutshell here, really quickly. Okay, this is why I can only work with insulators. Okay, so now let's talk about the Van de Graaff generator. Because I think it's a good way to bridge between what we're talking about, which is areas of static charge with fields around them, and it's easy to demonstrate some of these concepts with it. So a Van de Graaff generator, it's really hard to draw a straight line with this thing. It looks kind of like this. Did we look inside the Van de Graaff generator? We'll take a look inside one in just a minute. It's too bad this isn't portable, or I could like add that part right into the lecture. Now inside the Van de Graaff generator, there's a little motor that turns an amber wheel. Actually, it's not an amber wheel, it's a felt wheel. Okay, so this wheel has felt on it. And inside the top, there's another little roller. Okay. No. I think it's important to understand how it works, though. And in between this is a latex belt. Okay. So what happens is, I'll just draw another side view of this. So here's this belt, because that's the sort of important part. This belt rotates. Okay. It rotates, and there's an interaction between the latex and the rollers. Right? What happens is at the top, the latex will pick up negative charge from the roller and bring it down, okay? And down here at the bottom is a comb. I'll show you all this stuff in just a minute. And that comb is connected to ground. So as this negative charge comes near the comb on its way down, on this conveyor belt, it'll actually be able to leap this gap and ground itself out. Okay, so this negative charge is brought down away from here. It'll actually ground itself out and leave the system. Okay, the ground on there is the third prong on the 3-prong plug. Okay, the actual connection to an electrical outlet with this is only, so you don't have to crank it with your hand, right? It's only to power this thing. Van de Graaff would work if you hand cranked it, as long as you had a ground out off the little comb, which I haven't drawn here. So there's the little comb. We'll take a look at that. Okay, so where does this negative charge come from? Well, it turns out that there's also a comb up here. Okay, so there's a comb up here. It also turns out that this guy pulls some electrons out of here as well as they jump onto the comb. So you get some positive charge traveling up the other side. Okay, as the positive charge swings by, that sucks some electrons off the ball here, and they ride on down and leave the system. So the overall effect of this then, by pulling electrons out of the ball, is the ball ends up with a big pile of positive charge attached to it. Okay, so I think that's a good time to just break